Welcome to this IOP Domains video on nuclear particle physics, introduced by me, Nikki Thomas, and Gary Williams. This video is about the Standard Model of nuclear physics. The model was developed to explain experimental observations made during high-energy particle collisions. CERN is Europe's largest nuclear physics research institute and uses particle accelerators to uncover what the world is made of and how it works. This image from CERN shows the production of top quarks. You can't see any particles, but their tracks provide so much information we can work out what particles are produced and their properties. Teaching particle physics using resources from organisations like CERN is a fantastic opportunity to introduce students to cutting-edge research. The Standard Model is so abstract it can be useful to introduce it like a story, basing it on a theme which builds on existing knowledge, for example using size or scale, or a historical approach. Interactive animations, videos like Powers of 10 and comparisons can all help to reinforce a sense of scale.
This topic can be difficult to teach because the experiments we can carry out in school laboratories are very limited. You may find it useful to include some simple games like Snap, Top Jumps or Guess Who games just to try and help students get familiar with some of the many different terms that are introduced in this topic and to increase the variety of activities in lessons. At some point, it might also be worth pointing out what this model is trying to explain. What makes science unique as a way of knowing is experiment. The experiments we're talking about in this context are basically those where a known stimulus is targeted at an unknown item and the characteristics of the item are worked out from the way the stimulus responds. These could be called black box experiments and are similar to the way we model Rutherford's experiments to determine the structure of the atom. There are a number of black box activities online as well as those involving electrical and optical unknowns. Or, in this hands-on activity, students roll a marble down a ramp and it goes underneath a pie tin and bounces off a shape that the students cannot see. From the path of the marbles, they should be able to work out what the shape of the hidden item is.
Students can use data to prove that the density of the nucleus, from the smallest to largest atoms, is roughly constant. In these images, ball bearings are used to represent nucleons. I've added a small strong magnet so the ball bearings have clumped into approximately a sphere, my model of the nucleus. A chlorine nucleus contains 37 nucleons of mass m and volume v. It's fairly easy to see that its mass must be 37 times the nucleon mass and its volume approximately 37 times the nucleon volume. Using these approximations to calculate density, mass over volume, then the number of nucleons will cancel out and the nuclear density is approximately constant for all elements. Experimental measurements showed that atomic radius is approximately proportional to the cube root of the mass number A. This makes sense as the volume of a sphere is proportional to the radius r cubed. For a nucleus of chlorine containing 37 nucleons, the atomic radius is approximately 4 femtometers. A femtometer is 10 to the minus 15 meters. On the atomic and nuclear scale, the Standard Model presents matters so very differently to before, so many terms will be unfamiliar to your students. Particle physics includes the study of particles that make up matter, and these particles are called fermions. It's worth reminding students we're looking at a model. In the same way as they model electrons and particles as waves, and using energy levels, shells and clouds, we'll use different models to explain different phenomena in the nucleus. Fermions can be split into two groups. Particles formed from quarks called hadrons, and these include protons and neutrons. Particles that don't contain quarks are called leptons, and these include electrons, muons and neutrinos. Both leptons and quarks are fundamental as they can't be split any further. Hadrons, which contain quarks, are not fundamental because they can be split. Make sure that students realise leptons just don't contain quarks at all. And by the way, is it quark or quark? It really doesn't matter. Hadrons can be split into two groups. They can be formed from 3 quarks, groups of 3 quarks, and called baryons. These include your particles such as protons and neutrons. We have also found mesons, which are formed from a quark and an antiquark, but these are extremely unstable. The Standard Model includes 6 different types or flavours of quark. They can't exist on their own and they're found in groups of 3, or paired with quarks and antiquarks. Antibaryons are particles formed from 3 antiquarks, and we'll talk about antimatter in a bit. Quarks all have a baryon number of a third. Baryon number is a quantity used to differentiate hadrons from leptons. Flavour is used to differentiate quark types, and these flavours can be up, down, charm, strange, or top and bottom. They're just a distinguishing name. They're not linked in any way to actual physical properties. And quarks have an electrical charge of 2/3 or minus a third. All of these properties are conserved, and the rules of this model mean that only certain combinations are allowed. For example, the total charge and baryon number has to be an integer whole number. Protons and neutrons are very familiar. The proton has 2 up quarks and a down quark. A neutron has an up quark and 2 down quarks. Beta decays when one quark changes flavour. For example, a down quark turns into an up quark during beta minus decay. Pupils have already been taught that the beta minus particle is an electron emitted from the nucleus during beta decay. Make sure they understand the nucleus doesn't contain electrons, that the beta particle is the product of nuclear decay inside the nucleus. The Standard Model also needed to explain why quarks were only found in groups of 3 as baryons or as quark-antiquark pairs. To solve this, the Standard Model hijacks the word colour. It allocates a colour charge to all quarks. They're not actually coloured, and the colour isn't fixed for a quark. It changes if the quark combines in a different particle. Quarks are allocated a colour charge of red, green or blue. A baryon must contain a red, a green and a blue quark. The thinking behind this label is that red, green and blue light mixes to form colourless white light. So baryons containing 3 quarks have no colour charge. You may come across resources that use coloured images to represent different quarks. The actual colour is not relevant. It's just a label, and you can easily avoid using or referring to colour unless it's specifically mentioned in your specification. To bring a model to life, we use analogies where we substitute something with similar properties to the one we're describing. Many quark analogies involve Lego. There are similarities. Quarks and Lego are basically indestructible. They can be used to build larger structures, and each block is distinguishable. For example, I could use a yellow block to represent an up quark and a blue block to represent a down quark. So if I have 2 down quarks and an up quark, I could represent my neutron. If I have 2 up quarks and 1 down quark, I could represent my proton. To make this analogy more useful, you can add labels to each block using stickers or pens, and then pupils can model some of the rules, like an integer baryon number, integer charge, or even strangeness. So you can see what I've done here. I've got my baryon number, labelled it a down quark. I've got minus a third. So I can maybe create my neutron. And here you can see I've got a total baryon number of a third. I've got a total charge of 0 because I've got a charge of plus 2/3, minus a third, minus a third. And I've also labelled these as up, down, down. And I can do the same with my proton, up, up, down. I've got my 3/3, which is my baryon number, and I've got 2/3 plus 2/3 minus a third, a total charge of +1. However, there is a complication you may see when you view images of baryons and mesons, which are built using Lego, especially when we're working with specialists, nuclear physics specialists. Most specifications don't include colour, but scientists using Lego often use a red, a green and a blue block for each baryon. So they will create something like this, but they will maybe add a label and say, well, I've got an up, up, down quark. However, students might be more likely to do what I'm doing here, which is to think, well, actually, a yellow block is an up quark and the blue blocks are the down quarks. So a possible solution to that is to maybe add labels here. So I've just made sure that each one of my quarks does include a red, a blue and a green coloured quark. Now, colour is something that can change as quarks move between different particles. It's not intrinsic to the quark itself, but we do end up wanting to have this combinations which are colourless. In other words, a combination of a red, a green and a blue. Another discussion you might have is what colour should you use for antiparticles. I like to think of maybe a particle being black and the antiparticle being white. So I could say I've got a particle and an antiparticle here. However, what I tend to find is modellers using complementary colours. So they might say the antiparticle of a yellow up quark would be a blue down quark. Quarks are affected by all fundamental forces. They have charge and feel electrostatic forces. They have mass and they feel gravitational forces, although this is quite negligible compared with the other forces. As quarks, they feel a strong force which binds quarks in the nucleons and binds nucleons into the nucleus. They also experience the weak interaction. The strong force is very short range. It's repulsive, less than 0.5 femtometers. A femtometer is 10 to the minus 15 meters. And they're attractive up to 3 femtometers. One way to simulate the strong force is using rubber bands to hold 2 pens together and try pulling them apart. The strength of the strong force increases with separation, so above 3 femtometers, it's actually too strong for quarks to separate. Students can feel a similar effect by making an analogy between the elastic force and the strong force. So if they try pulling these pens apart to draw lines, beyond a certain range, it's really hard to do that because these elastic bands are pulling back too hard. Going too far and the bands will snap. The drawing will show an inner limit as well because the pens just can't get any closer. For quarks, the inner limit's a different reason, is because the strong force is actually repulsive. So if you watch me drawing around here, and you can see that picture. Antimatter is an intriguing but potentially misleading name. Antimatter particles do exist, they're not just science fiction, and they are real particles with mass. They're naturally produced in beta decay, cosmic rays, and galaxy cores. Both leptons and hadrons can exist as antiparticles. Positrons, the antiparticle of electrons, are used for medical imaging. Some antiparticle properties like charge, baryon number, strangeness have the opposite sign compared to their matter particle. The table compares the properties of the up quark and the anti-up quark. Notice that the antiquark is indicated using a quark symbol with a bar drawn above it. Antibaryons are made entirely of antiquarks. For example, the antineutron contains an anti-down, and anti-up quark. Antiparticles don't attract matter particles, but if they meet, they annihilate and their mass is converted into photons. So mesons, formed from a quark and an antiquark, are very unstable with very short half-lives. Thank you for watching. We really hope you found this video on nuclear particle physics helpful. Don't forget to check out our other domains videos at spark.iop.org.